Section: Introduction. In this section, we discuss the advancements in large language models, LLMs, which have been driven by increases in the number of parameters, the length of context, and the size of the vocabulary. As LLMs have expanded, so has the necessary infrastructure. We utilized large mini-batch gradient descent and data parallelism to leverage growing computational power. The zero technique allowed us to decouple the number of GPUs from the memory needed for model parameters, gradients, and optimizer states. Activation checkpointing helped us reduce memory usage for activations, enabling the creation of deeper models. Flash attention improved memory efficiency in self-attention, reducing its complexity from quadratic to linear, which allowed for longer context windows. These enhancements have shifted the memory demands of LLM training primarily to the cross-entropy loss, which consumes a significant amount of memory, up to 90%, and grows with the product of vocabulary size and the number of tokens in a batch. This issue is becoming more pressing as even the largest vocabularies may still need to expand. To address this, we propose a new method called Cut Cross-Entropy, CCE, which has a minimal memory footprint and can scale to very large vocabularies. Our main insight is that the computation of the loss and its gradient relies only on the log probability of the true label. By reformulating the arithmetic, we break down the cross-entropy loss into a multiplication involving an index matrix for the true label and a log sum express operation across all vocabulary entries for each token. Each of these operations has small, well-defined inputs and produces a single output per token. However, both operations depend on a large intermediate logit matrix that scores each token against potential vocabulary entries. We demonstrate that we do not need to store this logit matrix in GPU memory. Instead, we compute the logits on demand in SRAM using custom CUDA kernels. This results in a cross-entropy computation that has a negligible memory footprint without negatively impacting latency or convergence. In the related work section, we explore attention mechanisms, noting that the success of transformers has highlighted their computational and memory needs. Various alternatives to traditional attention have been proposed to reduce these demands. We focus on the classifier head of the model, which has not been the focus of previous studies. Additionally, we review efficient implementations of attention that address the high memory usage of LLMs. Some methods have utilized chunking, while others have split operations into two stages to optimize GPU memory use. Flash attention, similar to CCE, uses on-chip SRAM for parts of the self-attention matrix, which informs our memory-efficient cross-entropy formulation. We also consider vocabulary reduction strategies to lessen memory usage by limiting the number of active tokens. Some approaches have suggested hierarchical vocabularies or tokenization-free models that work with smaller vocabularies. Recent implementations have used chunking to lower memory usage in the cross-entropy layer, but this comes with trade-offs between memory footprint and latency. CCE aims to minimize both by relying solely on on-chip SRAM. Liger kernels efficiently use the GPU through chunking and simultaneous computation of loss and gradient, but CCE allows for user-defined transformations on the loss with separate forward and backward stages. In our preliminaries, we define a large language model, LLM, over a vocabulary, where the model predicts the next token based on the preceding tokens. This involves a backbone network that encodes the token sequence into a feature vector and a linear classifier that projects this embedding into the vocabulary space. The softmax function then generates probabilities from the unnormalized log probabilities produced by the classifier. Section Summary. In this section, we discuss advancements in large language models, LLMs, that have improved memory efficiency during training, particularly through our proposed Cut Cross-Entropy, CCE, method, which significantly reduces memory usage by computing loss based solely on the ground truth label without needing to materialize a large logit matrix. We also highlight how CCE builds on existing efficient implementations and contributes to minimizing both memory footprint and latency in LLM training. Section: Vocabulary. In this section, we discuss how large language models, LLMs, handle vocabulary. LLMs represent their inputs and outputs as tokens from a vocabulary, which we typically create using a method called byte pair encoding, BPE. BPE starts with all valid byte sequences from a standard text encoding, like UTF-8, and then identifies the most common pairs of tokens in a large text corpus to create new tokens. This process continues until we reach a set limit on the number of tokens. A larger vocabulary allows a single token to represent multiple characters, which shortens both input and output sequences. This compression helps the model understand better while also reducing the computational load. When it comes to inference, even with a large vocabulary, sampling from an LLM is efficient in terms of memory. The model generates one token at a time, calculating the probability of the next token based on the previous ones and sampling from that probability distribution. Since we only need the vocabulary distribution for one token at a time, the memory usage does not depend on the length of the sequence. During training, the LLM aims to maximize the likelihood of predicting the next token. The model can efficiently compute the necessary functions in parallel, but we need to save activations from nonlinear layers for later use, which can consume a lot of memory. To manage this, most training frameworks use techniques like activation checkpointing and specialized attention methods. Despite these optimizations, the final layer that calculates cross-entropy loss takes up the most memory. For instance, this layer accounts for a significant portion of memory usage in various models, with some models using up to 89% of their memory for this purpose. We also note that for a long sequence, the memory required can reach the limits of available resources, such as an 80 GB GPU. However, we propose a reformulation of the training objective that minimizes additional memory usage beyond what is necessary for storing loss and gradients. Next, we consider the cross-entropy loss for predicting the next token. The first part involves a vector product of embeddings and a classifier, while the second part is a log-sum express operation that does not depend on the next token. During training, we optimize all predictions together using a method called teacher forcing. This approach allows us to efficiently compute both forward and backward passes, leading to a memory-efficient and low-latency cross-entropy loss. Section Summary. In this section, we describe how large language models, LLMs, utilize a vocabulary constructed through byte pair encoding, BPE, to efficiently represent input and output as tokens, which reduces computational demands. We also explain our approach to optimizing memory usage during training by reformulating the cross-entropy loss, allowing for efficient computation while managing the significant memory footprint associated with large vocabularies. Section: Memory-efficient indexed matrix multiplication. In this section, we discuss memory-efficient indexed matrix multiplication. A straightforward approach to this involves either calculating the logits directly, which requires a lot of memory, or indexing into the classifier, which also has a significant memory cost. We combine the classifier indexing with the dot product of specific columns in a single CUDA Triton kernel. Our kernel retrieves the necessary columns from both the classifier and the embeddings, storing them in on-chip shared memory. It then computes the dot product and saves the result in global memory, using only on-chip memory throughout and avoiding any GPU memory allocation. To maximize efficiency, we perform operations in blocks to utilize the GPU cache effectively. We can also compute the backward pass using a similar kernel. We found it more efficient to merge this with the backward pass of the linear log-sum express operator since they share much of the computation and memory access patterns. For the forward pass of the memory-efficient linear log-sum XP, we implement a simple triple for loop. The innermost loop calculates the dot product for each token and batch element, while the middle loop updates the log-sum express across the vocabulary. The outer loop iterates over all batch elements. Parallelizing the outer loop is easy and can fully utilize the CPU due to the large number of tokens in training batches. However, achieving similar efficiency on the GPU is more complex. We first analyze how to efficiently multiply the model output embeddings with the classifier on modern GPUs. A common technique is to divide the output into blocks. Independent CUDA blocks retrieve the corresponding parts of the embeddings and classifier, performing the inner product along the specified dimension. Due to limited on-chip memory, we often use A for loop for larger dimensions, processing smaller blocks and accumulating results in shared memory before writing them back to global memory. This method effectively utilizes the GPU and memory cache. To compute the log sum XP, we apply the same blocking and parallelization strategy as for matrix multiplication. Each block computes a matrix multiplication, then performs the log sum express for its block, and updates a shared result vector. Since multiple blocks write to the same location, we use a spin lock on an atomic operation to synchronize these updates, which is straightforward in our Triton framework. Other methods may offer better performance in direct CUDA implementations. Section Summary. In this section, we present a memory-efficient approach to indexed matrix multiplication by fusing classifier indexing with dot product computations in a single CUDA Triton kernel, utilizing on-chip shared memory to minimize GPU memory allocation. We also describe the implementation of a linear log sum express operation that efficiently parallelizes computations across batch elements while managing memory access through atomic operations for synchronization. Section: Memory-efficient linear log sum XP backward pass. In this section, we focus on the memory-efficient backward pass for computing two gradient updates. We define the gradient as the product of the softmax of a matrix and the backpropagated gradient. Specifically, we calculate the softmax of the transposed matrix multiplied by another matrix, and then perform element-wise multiplication with the gradient. The backward pass involves two matrix multiplications, but we face challenges with intermediate matrices that exceed GPU memory. To address this, we recompute one of the matrices in the GPU's shared memory. We do not need to compute the normalization constant for the softmax, allowing us to efficiently calculate the softmax in parallel. We implement the second matrix multiplication in the main GPU memory to avoid the need for additional storage or synchronization of the softmax matrix. While a naive implementation requires no extra memory, it is slow due to repeated memory operations. To enhance memory access, we employ two techniques: gradient filtering and vocabulary sorting. Gradient filtering takes advantage of the fact that the softmax sums to 1, meaning many values will be negligible and can be ignored. We find that in practice, less than 0.02% of elements in the softmax matrix are non-zero, especially as vocabulary size increases. By skipping gradient computation for blocks with negligible softmax values, we achieve a significant speedup without losing precision. For vocabulary sorting, we aim to arrange tokens so that those with non-trivial gradients are grouped together. This minimizes wasted computation on partially filled blocks. We compute the average logit for each token during the forward pass and use this information to organize the vocabulary in the backward pass. This requires a temporary buffer but allows us to maintain a low memory footprint while ensuring efficient computation. Overall, we achieve a backward pass implementation that is both memory efficient and fast, integrating it with the forward pass for cross-entropy calculations. Section Summary. In this section, we describe an efficient backward pass for computing gradient updates in a memory-constrained environment, utilizing techniques like gradient filtering and vocabulary sorting to optimize the softmax matrix computations. By leveraging the sparsity of the softmax matrix and organizing the vocabulary to enhance computational efficiency, we achieve significant speed improvements without increasing memory usage. Section: Analysis. In this section, we analyze the runtime and memory usage of different implementations of the cross-entropy loss function. We focus on a batch of 8,192 tokens, with a vocabulary size of 256,000 and a hidden dimension of 2,304, which corresponds to Gemma 2, 2b. We utilize the alpaca dataset for our inputs and labels, along with the Gemma 2, 2b, instruct weights to compute the necessary components. Our findings are summarized in a table. The baseline method, which directly implements the loss in PyTorch, shows reasonable throughput but peaks at 28,000 megabytes of GPU memory for calculating the loss and gradient. Due to memory fragmentation, we find that computing the loss and gradient for the classifier head requires an 80 GB GPU. We observe that using Torch, compile reduces memory usage by 43% and computation time by 33%, highlighting the benefits of kernel fusion. TorchTune also offers a method that breaks the computation into chunks and employs Torch, compile, leading to a 65% reduction in memory compared to the baseline and a 40% reduction compared to Torch, compile. Liger kernels provide a memory-efficient implementation that also uses chunked computation, achieving a 95% reduction in memory usage compared to the baseline. However, this comes at the cost of increased latency, more than doubling the computation time. We note that the memory usage of CCE grows with the sum of the number of tokens and the vocabulary size, while the baseline and other methods grow with the product of these two factors. In practice, CCE maintains a minimal memory footprint regardless of vocabulary size or sequence length. Compared to the fastest method, Torch, compile, CCE computes the loss slightly faster due to not writing all logits to global memory and leveraging the sparsity of the gradient to skip some computations. We find that both gradient filtering and vocabulary sorting enhance CCE's performance. Without vocabulary sorting, CCE takes 15% longer, and without gradient filtering, it takes over 3 times longer. We demonstrate that CCE and other methods can be sped up by removing ignored tokens from the loss computation. Our additional benchmarks reveal that as the ratio of vocabulary size to hidden size decreases, CCE's computation time for the loss and gradient may increase, but it still saves significant memory. In terms of gradient filtering, we observe that the probabilities of vocabulary entries drop quickly, and for the top 100,000 most likely tokens, there is a linear relationship between the log of the rank and the log of the probability. By the 50th most likely token, the probability falls below our threshold for filtering, allowing us to exclude many values from the gradient computation without impacting the results. Finally, we demonstrate the training stability of CCE by fine-tuning various models on the Alpaca dataset. Our results show that CCE and Torch, compile produce nearly identical loss curves, indicating that the gradient filtering in CCE does not hinder convergence.